Okay, let's implement LSTM together. We first need to retrieve the parameters like this. This is going to be the shape of hidden states. We are going to concatenate all the hidden state in the forget, input, output, and other gates, stack all of them, and calculate the dot product together for computational efficiency. And then we slice this matrix, and the first H parts are for forget gate. And for gate, the next part. Okay? The I input gate times H, 3 times H. And the last out, like this. Okay? Rather than calculating FGIO separately, we concat them all and calculate them here, and then we slice them. This way, we can reduce the computation. Okay, then we calculate the next cell state, F times C pref plus G times I. H next, it's going to be O times MP10 H C next. And the cache, we're going to store X, H pref, C pref, I, F, G, O, C next. Then we return H next and C next. And backward might look a little bit complicated. We first retrieve the parameters. I, F, G, O, C next. What we are going to do is calculate tangent, hypertangent C next. Then we are going to calculate this intermediate gradient. Let's have a look at this one. So what we are doing is calculating gradient at this point. C next comes here, H next comes here. Okay, so that's what ds is about. After calculating ds, we can calculate dc pref. That's simply ds times f. di ts times g. I, g, they are exchanged when calculating gradients. F, O are here. So think about this image first. The F, ds times C pref, DO, DH next times 10H C next, DG DS times I. And the next step is I times 1 minus I. The F times 1 minus F, the O, 1 minus O times O. This is to consider the sigmoid function, e.g. 1 minus G squared. After that, we stack A. Then we can calculate the gradient of dWh. dWx becomes NP dot x transpose dA. And we store these gradients. H 1, 2, B. dx becomes NP dot dA Wx transpose dH pref becomes NP dot dA WH dot transpose. Then we return dx dH pref dC pref. Okay. Let's summarize what we've discussed. Today we discussed rnns. rnns allow a lot of flexibility in architecture design. And vanilla rnns are simple but don't work very well. You can only account for time steps of 10 or 20. So we commonly use LSTM or GRU. And backward flow of gradients in RNN can explode or vanish. And to solve the problem, we introduced gradient clipping or different architectures like LSTM and GRU. And better and simpler architectures are a hot topic of current research, as well as new paradigm for reasoning over sequences. Nowadays, we use transformers. No RNNs quite a lot. However, if we don't have much computational resources, then we cannot use transformers. In that case, we need to use RNNs. And better understanding, both theoretical and empirical, is needed. Okay, that summarizes this session.